Welcome back to class. So our third lecture, or second lecture of the day, third lecture of the summer school, will be focusing on MPC, model predictive control. We'll start with, I believe, two hours of theory, and then we'll jump into an example. So the lecture will be provided by Professor Iman from the Australian National University, where he leads the Cicada lab. So Iman, the floor is all yours.
Thanks, Anton, and thanks for your time. Please interrupt me whenever I say something that is meaningless. I say a lot of those things. And you have to remember, practical from my point of view might not be very practical from your point of view. It's just about what I say. Okay, cool. So what I try to do, the first part of the talk would be a bunch of philosophical pontification of how I think people should approach solving certain set of problems. The middle bit, I talk about how one way of incorporating uncertainty problems. And the last bit, really, I'm thankful to Andreas because he covered a lot of things that I would need to cover to be able to tell that story. Now he's done it. So I'm going to tell a story, which is almost, it's along the same lines of argument, but with an emphasis on application to optimal control. And optimal control is anything, if you ask me, that has an element of time and dynamics to make decisions that propagate across time. All right. So that's just the brief outline of the talk. I start with this spiel about hierarchical control architectures, why I think it's important, and why we do it, sometimes even without realizing it. Then I talk about model predictive control, or MPC. Some people call it receding horizon control. Then I talk about uncertainty and this aware control framework, and then elements of that. I talk about the structure exploiting methods for solving MPC problems, and then I conclude with a bunch of, again, thoughts and really starting points for this further discussions. All right. There are a bunch of disclaimers as well. The start of the talk is informal. I'm not gonna, it's not a rigorous talk. So I overload variables. I wave my hand to make the difficulties disappear whenever I want. Obviously, they don't have crime. And I think the general ideas are more important than the actual details. If I manage to spark some interest in some of you to go and delve deeper, then I achieved what I wanted to do. And that number really sits around 10%. That's the objective I have in my life. 10% good enough. Another disclaimer, there is this Canadian connection. Donald Harmon Atkinson, he's a classicist from Queen's University. He has a great book called Surpassing Wonder, the invention of the Bible and the Talmud. And that's in the introduction has this line, which is great. It's from the Common Book of Prayers, 1662. It's one of the most depressing things I've read in any book, that an author begs forgiveness for any mistake that they're going to make. And they're going to disagree with me, but I tried. So have that in mind. And how do I go to the next slide? Here we go. Okay, so I'm going to start very abstract. I'm going to start with some generic dynamical system S. And I talk about a different dynamical system, I call it E. Now, S for the system, E for the environment. Both of them are dynamical systems. So now can someone tell me when I say dynamical system, what do I mean? Or what would you think of it when I talk about dynamical systems?
Derivative terms.
That might be that, but what is derivative with respect to what? I think that time. So it changes in time. Starts from somewhere, goes somewhere in the future. And often, under a bunch of other set of assumptions, we have this implicit Markovian assumption that whatever we know about it now is enough to predict its future. Okay? So that's what I mean by dynamical systems as well. And we always, now if you really talk to hardcore people in dynamics, there is this war been raging for decades and no one really cares about it except maybe 20 people. We talk about if the dynamical system has an input one, and what is the meaning of an input, and what is an output? Well, let's not worry about it. Input is what we feed it, output is what we're going to get out of. But broadly speaking, each system, the input being fed into a system can be categorized into two sets. The things that we do it intentionally, and the things that we don't. So the inputs, I call them U, and the other one I call E for this term. And again, as an abstraction tool, it's just the coupling between the environment and the system. Okay? I call a variable X to correspond to the state of the system. State is memory. And whenever I talk about the state, I talk about memory. And there is this other thing that even the environment might be influenced by this other variable. These are these things that might come from somewhere else, other systems interacting with the environment, etc. Again, I use another Canadian connection here. If anyone has read Bruce Francis's Guide to Technical Writing, has anyone read that? Does anyone know who Bruce Francis is? Good, yeah, good. So Bruce Francis has had this technical guide to writing, and he loves, he promoted this way of writing technical statements. And what it means is, given some potentially infinite time period, t. Now, let's not get into what is the meaning of time as well, but it's okay. And then some constraint set, yt. I want my system for all that time in that interval t to operate to satisfy those conditions. So what we call it is constraint satisfaction. I don't want to violate constraint. I don't want to, because I might call it security, I might call it whatever. I don't want to violate certain set of constraints. I might have a different objective as well. I might care about performance. Maybe I want to minimize the cost of some dynamical systems. Maybe I want to minimize the cost incurred by the environment. And remember, I'm arriving at it from a very engineering point of view. I don't care about it. Costs are mainly made up. I care about satisfaction, about meeting specifications. That's why I put that as primary. Okay? So given some uncertain model of E, some measurements, and some requirements. Requirements are really things that set those constraints that we want to operate. So that would be the role of the control system that takes the measurements out of a measurements machine, you call it a sensor, and the specifications given to it to interact with the environment and the system so that things are hunky-dory. So this is the broad structure of the problem. Okay. Now let's just tie every random stuff together. So if anyone has read Daniel Kahneman's Thinking Fast and Slow book, which is really a good book, but he could have written it in 20 pages instead of 300 pages. It's the same thing repeated over and over and over and over, which is really just one paper he wrote 20 years ago with his co-author, Kavitsky. But anyway, the whole idea is human brains operate on the two systems. One system is quick and automatic and messy. The other one is fast. The other one is ponderous and takes efforts to make better decisions. System one is fast and makes mistakes, but it's also very energy efficient. It doesn't consume much. And for most of the things that we do, it's good enough. The role of the second one second system is just to make sure that system one is not always in charge of making all sort of decisions, potentially really bad ones. Okay. So there's nothing new under the sun. It's another depressing thing by allegedly Solomon, who knows? So we can think of this sort of a multi-layer type system as well. I have a top layer, now I call it P, surprisingly for planet, that exerts influence over the operating environments and couples with the controller, the lower level system. And then all of these things interact with the lowest level of the system, which is the dynamical system. Now, there is another thing I beg you to remember. Each of these are dynamical systems as well. They have memories. The impact of planning reveals itself in the future. It's not this magical thing that comes out and you implement it and done. This is something that is lost over, especially over the last maybe 10 to 20 years, since the computers became super powerful. People don't care. They think just everything is in this input-output maps, static maps. That's not the case. All of us going to die if we keep doing it. So it's a hierarchical structure. A flattened approach is hopeless because in a way we are not taking advantage of some intrinsic property of the system that not every piece of information needs to be available to everyone. Information should propagate through multi-layers, and you have to use what you need to use at the level that is appropriate. We can think of this hierarchical structure as systems that operate across different computing scales, but now the problematic term I'm going to use is information as well. It operates across different information levels. Now we can become very precise about what we mean by information or not, but that's take the intuitive view of that. And then we have to be careful about the whole interconnection. How would a decision made by a planner shows itself after it goes through the controller, propagates through the system, and comes back up? So it's something that we have to be really careful how we do it. Again, with the emphasis of the control actions impact the universe, and then we have different information types and different qualities and different levels operate at different times. So the example of, again, in the power systems, I think it was from the 1990s that there used to be these low-level PID type controllers, and then they started having markets replacing the low-level controllers through the operation of the grid. And I think that was a mistake. Again, as an outsider, I can say things, whatever I want. Because then we really flattened everything. We decided to use a hammer that is useful for a particular type of name to use it to beat every single hammer that name that is. So planner input might have considered these requirements and then some coupling. We really think of it as operation profile for the low-level controller. And the low-level controller is going to use those. Takes these measurements from the planner, tries to reject disturbances applied to the system, and tries to drive the system to where it needs to. I forgot to put another reference. If anyone has read, or if anyone hasn't read Richard Hemming's book on the science of writing, science of the art of science and engineering, something like that, I really recommend it. But if you spend a lot of time reading that book, the whole thing boils down to something that is very intuitive. Whatever you want to do, we have to avoid being surprised by what we do. So if you ever try to sell your work as something with emergent behavior, step back and say, did I mean that to happen? If not, it's probably not a good engineering work. But this is forgotten as well. Now it has become a virtue a bit. There are multiple ways. Two ways to approach design is to really have this thing that people often call time scale separation or information scale separation, to pull them apart. And then maybe we have to think about it a bit more in terms of modularity of separate things, subsystems from each other, to really be able to have a plug and play view of the system that we work. Yeah.
M is the measurements of the system, is that right?
M.
For M at the very bottom.
Yeah, M is the sensor that collects information about maybe the disturbance or from the state of the system.
So you don't measure the environment directly, you just measure.
You might not be able to. So I can be cheeky and have a pathway that directly goes through here, but not necessarily. I don't have access to everything all the time. So one thing is one cannot solve flat problems. When we squish everything in the same level, it becomes intractable. And again, Andrea's example was exactly that. And the reason that they approach work was they found a clever way of separating the things that make things unnecessarily complicated from the things that are the important bits of the solution. So whenever you can divide and conquer, do it. The other message is, I will come back to it, if there is a structure, exploit it. So that structure can be temporal, can be spatial, can be all. Having the domain knowledge might help you identify structures, but sometimes it can work as an hindrance as well. It might blind you to certain structures that someone else might observe. So whenever there is a structure, exploit it. This is particularly for students. Don't throw solvers at problems until one sticks. And then whenever you deal with and use the term uncertainty, be a bit careful as well what you mean by it exactly. Because again, it's a catch-all phrase that people just use. And thinking of systems as interconnections through zooming in and zooming out is helpful. Sometimes if you go and look at it from a bird's eye view, you might observe things differently than when you focus super hard on one component of the system. All right. Now, after all of these philosophical stuff, and it's good because you're stuck here, you can't run away with it. So let's just become a bit more concrete. So one way of implementing controllers is to think of things as optimal control problems. So the aim is to compute a controller feedback policy that maps the state of the systems into control limits. So that's the overall goal. So one way to look for policies, to be able to differentiate different policies, is through the machinery of the cost. And really try to optimize. Okay, when I say trajectory, it's a very meaning-laden word. It means the behavior of the system over a period of time. So whenever I talk about trajectory, that's what I mean. It's about the trade-off between short and long-term benefit. And what it ends up looking, a typical optimal control problem has this structure. It has a bunch of costs for different time steps. Because it's a dynamical system, it has to start from some initial condition. It has an equation that describes its dynamics. There are a bunch of constraints that the states has to live in and the control has to live in. And then what we really want, that's the state feedback structure, that given the state that we are, we want the input that we generate to be a function of that set. But you're after a mapping. And really the problem here, you're looking for that particular mapping. So, I mean, the spoiler is here. Because you're looking for a mapping, think of it as a function, lives in an infinite dimensional space. So if you want to search over the space of functions, it's really, again, impossible to solve. Because we have, in the absence of any other simplifying structure, this problem cannot be solved. How many of you have seen a problem like this? Okay, good. At least around 50%. So I'm not. So before continuing, what should we aim for now? I just gave you a bunch of bad news back to back. Can someone tell me what we can aim for? I'm not even wearing my glasses, so.
Linear policy.
That's one way. What is special about the linear policy?
Easier than any function.
Yeah, it's easier. So what does it do? It approximates things. So we cannot solve the hard problem. What we do something that's just good enough. But we have to define what we mean by good enough, right? We don't know that. But let's see. So this is where this model predictive view of the world is useful. So if anyone is interested, these are a bunch of references that you might consult. Probably the best book on it is the fourth or third edition of it. It used to be a book by Rollins and Main, but then Deal joined in the last edition, just before David Main passed away. It's for general model prediction control issues. Lars Gruner and Jürgen Panek, they have a nonlinear model predictive controller. It's a bit more technical. And then Borelli, Bemperad, and Morari, they have the other book that really focuses on linear systems, but then moves to hybrid systems. Tobias Geyer has a very specialized book on application of MPC to power electronics application. But again, maybe if you're really interested, that would be, I would recommend this to be after you read one of these. It doesn't, this book doesn't require you to know the theory here. In fact, it's in terms of theoretical foundations, it's very audacious, but it helps. I mean, it helps us get it. Okay, this is a picture that you will see in every MPC presentation you've ever attended. Or I don't know if you ever looked, but it's really, but it's good because it talks about how the system really works. So we have the plant, this is the system. It has outputs, it has measurements, and then we have something that's called the optimizer, the controller. The controller gets a reference, which is really one of the specifications. It might be given the objective, that's the cost you want to minimize, the constraints, and some model of this plant. Doesn't need to be the same thing, obviously, because we never know what the plant is. It's a model of the plant. And then what it does, over some finite horizon, it calculates a plan of how things ideally would pan out. It implements the first step, and then sits back and observes what happens to the system. Collects measurements again, and then devises a new plan. implements the first step. And ad nauseum it continues. It's really what a receding horizon strategy. That's the first people who came up with it. They called it receding horizon, or MPC. It's just a tractable approach to come up with a approximation of an optimal feedback policy. What it is, it's a feedback policy because it collects measurements and it proposes an action. The action goes through the system, goes through the system, measurement is collected, and we keep repeating. Okay, now, so what we really want to do, we want to now simplify our lives a bit. So there are a bunch of things that are different between this formulation of the problem and what we saw in the previous slide. That is yellowy, orangey color. There are the differences. The first one is the top here used to be infinity. Now it's n. It's a bounded integer. We've added a terminal cost, and we've added this terminal set. So we really have added this. So what this one does, the terminal costs, because we've truncated, we've chopped the tail of the infinite horizon cost. The idea is that we put everything in the terminal cost. Right? And then this terminal set as well, it tries to be yet another way of capturing all the other constraints, all the other things that we chop, because now we only enforce this constraint satisfaction over the horizon. So we put that to capture everything that we have chopped out. I've moved to linear dynamics. It doesn't need to for now. So what is the fundamental thing that has changed between this problem and the previous one? Think about the decision variable. Okay, let's go back here. How many decision variables do we have here? How many decision variables do we have there? Finitely many. So that's the key difference. So what is the price that we pay for moving from infinitely many decisions to finitely many decisions?
And only have the projection in that space.
Projection is a very dangerous word, but I understand what you mean.
You have to approximate the file, so you lose information.
You lose things. You sacrifice performance and potentially constraint satisfaction. Okay. Now we can. Again, I like putting things in block diagrams. They look better. So I have a plan. Now that's the inside of that computer that we saw. And I love using ticks. You have no idea. So I have a plan. The plan does stuff. We observe it. And then we plug it in some new optimization problem. It's a nonlinear program now. And then you can solve it and see what happens. So there are a bunch of things that are important. Here, for simplicity, I'm putting measurements, but it doesn't need to be the measurements of everything out of the plan. You can put an estimator there, in principle. That estimates the things that we can't directly observe. Then we can solve a finite time optimal control problem. Find the optimal input sequence for the entire planning window, and then implement only the first control action. Again, this is a spoiler, but think about it as an engineer who wants to deploy this in the world on a system. what is one of the challenges just from an implementation point of view that you have to remember? The keyword is not quiz.
Samsung.
Yes. You have to be able to sample fast enough and pass the information to the optimizer fast enough, and the optimizer should pass a new input fast enough. So that's a challenge. There are ways around it, and that's people have made careers out of it, but that's a very important thing. Forgetting all the other things that can go wrong, you might not be able to give the plant a viable command in a timely fashion. I'll come back to it. Just a simple example. It's a very simple scenario. It's because, and it's a bit more, you can think about things that move a bit easier than electrons. But they really don't move. There you go. So if I have a flight ceiling of some quadcopter, this is when quadrotors were just used for humanitarian application. So we have a planning horizon N, and we might plan N a step ahead. And then we execute the plan, and we might follow the plan. So maybe we were there, and we came up with the blue plan. We implement the first stage of the plan. Will I ever arrive at where I expected? No, because my models are garbage. Always, your models are bad, but sometimes they're good enough. There is this, again, this view that we need more complicated models because that predicts things better. No, it doesn't. Well, you ask yourself, what do you want to do with that model first? But that's one thing. The other thing is that there are all these exogenous inputs that you have no control over. Wind flows, how do you know? So you will never arrive at where you expect. So that's why you end up doing replanning again, and then you implement. And that's the principle of the feedback. And you keep doing it. Okay. So now constraints in control. So all physical systems have constraints. Early electric circuits, they have bandwidth constraints, for instance. And that's why the frequency domain analysis taken to be. But yeah, we always have constraints. Any physical system has constraints. Physical constraints might be like actuator lengths. Performance constraints might be things like overshoot. I don't want my power that I inject into the system to pass its circuit. I don't want to go higher than a level. And I might have safety constraints. This might be performance desire. I don't want ringing in my system. But there might be dangerous things as well. I don't want things to blow up. So traditionally, when we would have a controller, we might have a behavior like an orange curve. It would be a set point tracking, so like a step response really. But we might have a constraints that then this would have violated, and we would spend a lot of time tuning the gains of the controller so that we end up with something that doesn't violate that particular one. So that's constraint management, and those guarantees are not really straightforward. It becomes a bit of an art. And it only works if the set point is sufficiently far from constraint. But most of the time, if you are, for example, if you are driving a car and we really want to take performance out of it, we push against those constraints all the time. We want to operate close to the constraint. That's where this sort of classical ways of designing controllers didn't really, they're not amenable to solve those sort of problems. So that's one good thing about MPC. It explicitly considers constraints. It has this intrinsic incorporation of a notion of cost. And hopefully, if you do your math right, you end up with some stability and constant satisfaction guarantees. Even if you don't do your math right, you almost surely will get them. Okay, bunch of history. Because it's not a new idea. It's been around for decades. So this automation and remote control was the Soviet journal, equivalent of automatic control for IEEE. So the first mention of it came at yet used in a program. And then Richelieu had this paper in Automatica in 78. So this is the first time that something which is like a model predictive heuristic control appeared in the Western literature. It had a whole bunch of different names, identification and command, impulse response, so it does all of these things. And these are these properties that it has, the quadratic performance, wouldn't really handle constraints, and the controller was not a transfer function. So that was, when something is not a transfer function, you can't implement it using analog circuitry. It's 1978. You have to implement everything using analog circuitry. There was this other paper in the 70s, late 60s, a PhD thesis that talked about similar things as well. It was implemented in petrochemical industry. And for around 30, 40 years, that was where process industry was the only place that MPC could be implemented. Now, why do you think that that was the case? I've given you the answer there, probably, but no, I haven't. Yeah.
Could it be because of the time characteristic? It was slower.
Exactly. You need to make a decision every 24 hours. Even if you do things by hand, in 24 hours, you can do it. And then mid-90s, we started realizing that it has properties. We talked about robust MPC in the noughties, and then in the teens, stochastic MPC, and then distributed versions of MPC and all sort of things. Now, just time scales of the applications that now these days people use MPC for. In computer control, decisions have to be made in nanoseconds. Power systems, you can move between microseconds to hours, depending on the level you're operating at. Motion control, CNC machines, milliseconds, building energy management, seconds to hours, engine control, again, milliseconds to seconds. Irrigation channels, really, just seconds to days. Yeah, this is the last one. It's just low-level controller, and then refineries, again, order of days and hours. So we'll have two examples of things that I've been involved in implementing it. One thing was there are these, I mean, in Canada, so you have a notion of size of the place. Farmers ask for water, then the water source is 700 kilometers away. Something needs to be released from the upstream, takes a couple of days to arrive at the farm. So this is a challenge, right? Because what do the farmers do? They want water at the same time. Now, what happens if you release all the water they ask for? It floods everywhere or gets wasted. So one intuition is that you have to separate them apart. But then what happens to the farm? It's not going to receive the water when it needs it. So that was the problem that they had, and we looked at different ways of solving it. We ended up doing a whole bunch of a multi-level approximation of a very hard infinite-dimensional problem to some solvable problem. The other thing for you, Anton, it's one of the works I did with Anton many years ago. It's just about the multi-energy building to grid services, you might have different time scales that you might predict sometimes between a longer time scale and a shorter time scale for making different levels of decisions. The top level decisions might be things like, what is the state of my HVAC? Do I turn on things or turn them off? I have a battery storage. I have a thermal storage. I do all of these things. When do I turn things on and off? So there are a bunch of integer constants. So this is just an example of, I plan things with task steps in the future. And then within those longer planning horizons, I might make decisions within the shorter times. So you can go and read this fine paper. All right. So advantages and disadvantages of MPC. What it does well, it allows you to encode models, linear models. Performance is related to the objective function, so you can encode the performance, and you explicitly handle constraints. You encode them directly. And you do control some iterative resolution of the problem. Now, it has disadvantages as well. Nothing is always good. One thing is, it's computationally expensive, potentially. So you need really spend time understanding what sort of algorithm to use to solve these problems. That satisfying in real time is a dangerous word too. But again, something makes sense to satisfy real-time requirements. So that's again implemented on the system. Okay. Now, does anyone know who Lloyd Trefethen is? Okay. Anyone who doesn't, go and read about Lloyd Trefethen. He has a bunch of maxims. Lucky I have it by that anyway. I like all of them. This is particularly good. 9. The fundamental law of computer science. As machines become more powerful, the efficiency of algorithms grow more important, not less. Because it leads to laziness when we you can get away with things. Yeah, it's very good. Okay. The other thing is that it may or may not be stable or feasible. So you might eventually get to a point that you cannot come up with a control that satisfies the constraints. So this is the notion of recursive feasibility. So if you're not careful, that's dangerous. Now, for certain systems, you actually can drive your system to instability as well. And instability in a dynamical system point of view, in a way that the states become unbounded. The other thing is that this transient response is not well understood. It does all sort of weird stuff until it gets to steady state. So how you can get around it is sort of these things that are called inverse optimal control, and then in certain circles, it's known as learning from demonstration. That's where it's in a way you try to encode some domain knowledge back into these algorithms when selecting appropriate costs that mimic the behavior, a desired behavior that a particular expert might like. Okay. So as I said, introduce terminal costs and constraints. We capture the feasibility and the stability side of things. And then really how can we pick these costs to get the performance that we want. It's just saying the same thing from the last slide. There are two ways of thinking about MPC implementation, direct and indirect. Direct is when MPC is implemented at the lowest level. So that's the real-time controller. Indirect is when it sits at the planet level. Almost any implementation of MPC industry, be it petrochemical, irrigation channels, that I know of, is indirect. It sits on top, and then there are often PID controllers that try to implement the plan that the MPC controller is giving them. Of course, you sacrifice constraint satisfaction guarantees, but you hope that as long as you tune those PIDs well enough, they remain close to the trajectories, and if you bake it enough buffer, you're fine. So it's similar to the idea of a reference governor, if anyone has heard of it. It came to be in control of synchronous machine reference governor. So what can go wrong with standard MPC? So there is no feasibility guarantees necessarily, and then you might not have stability. So if you have infinite horizon of like that, if you are when you don't have constraints and you have linear systems, and then the infinite horizon, infinite dimensional solution is tractable. Then if problem is feasible, then closed loop trajectories will be feasible. If the cost is finite, then the states will talk about the in finite horizon, it's short-sighted, tries to approximate that infinite horizon. But then, as I said, we might, after some step, we might not be able to come up with feasible trajectories. And we might not be stable. Okay, again. Focusing on the process of judgment or decision making rather than its outcome makes it possible to evaluate the quality of the judgment. That are not ex ante verifiable. Okay, some remarks on the stability. So these terminal constraints and the terminal cost, again, I keep repeating it, but the terminal constraint reduces the region of attraction. So if you put more restriction, then a controller might not be able to do its job properly. So it's, again, a trade like anything else. Feasibility would be at odds with just stability. So a typical way of circumventing the problem is to extend the horizon. So solve the problem over longer horizon. You do a shorter horizon. You get more leeway. Because again, intuitively what it means, you are not relying too much on your tail cost or tail constraint approximations. So are terminal sets used in practice? No. They are not well understood. You need to do a whole bunch of computation. Sometimes they become quickly intractable on a desktop computer. They reduce region of attraction. And it really sometimes, even a bad input is better than letting the system go open. And it's an often unnecessary consideration for off the shelf. If you have a system that is stable, which is almost any physical system would be stable, a long horizon would be good enough. Just increase the horizon. But the price that you pay is in the computation. Now talk about region of attraction to the point that you want it to go. It's very hard to characterize it. You can set this origin, really, just where the error is zero, error if you're tracking a particular input. The simplest, but you end up with a very small region of attraction. We can represent it for linear systems with quite a big cost. But again, in practice, and large horizon and check stability by sample. So start from short horizon, crank it up until you get somewhere that you like. As the horizon increases, the region of attraction approaches this object known as the maximum controlling dynamic. So this is the best as we get. It's a diminishing return after a certain threshold. Non-trivially, we can talk a lot about the linear systems as well. And what we've been silent about is the impact of disturbances and what happens when there are disturbances. The other thing that I have to cover is the time/effort needed to calculate. Now, going to be the break after this slide. Yesterday, Jean talked about it's bad to use fixed point iteration. There's a reason for it. Fixed points operation, they belong to a complexity class that is known as p-pad complete. Now, everyone has heard of that. No one really knows what it is. I don't think anyone can get that. But p-pad is one of those. So what it is, again, there are these other type of problems that are hard. And they are related to NP type problems. So, examples, this is how I was discovered. Finding Nash equilibrium. So the question of whether a Nash equilibrium exists for a game is not NP hard because we always know the answer is yes. But the question if there is a second one is NP hard. A Nash equilibrium is a fixed one. There are other p-pad complete problems. Again, finding Nash equilibrium, computing fixed points in Breuer functions during a business tool. So all of these things are really market economics things. And the equilibrium of Arrow-Debreu is a p-pad complete problem as well. So if anyone is really bored and wants to study these things, I'm more than happy to work with them. They're so hard. I want someone else to actually understand it and tell me about it. Anyways. Okay. So enduring uncertainty is difficult, but large model is difficult. Therefore, also was onto something. So the truism is that you have to account for uncertainty, things that you can't quantify. Most existing LORER, they don't do it. And what happens in the end is either we ignore them or we assume they're Gaussian and then everything is fine. Most of the time, things that are really bad are not Gaussian. But the things that have long tail. The factor is low. So what a few years ago with a bunch of collaborators, we started thinking, and it's not just us. There were a bunch of different groups of people. And we started thinking, is it a systematic way to incorporate risk? The first person risk in decision making. Really, it comes out of mathematical finance. And Rockefeller is the one who formalized a lot of the mathematical framework for it. And if you ever looked at anything written by Rockefeller, it takes time to read it, maybe 2 years. But there's always a competition between weird stuff written by Nestrov and Nemirovsky and Rockefeller. Okay, so we're going to start from a very common way of incorporating some notion of uncertainty problems. Well, we might have a cost function, Z is our decision variable. Now, just in that setup, Z is the concatenation of state and the. So it's just again an abstract object. And we might have some constraints. And then there is this random variable. I'm not going to define a sigma as variable. Just it's something that we don't know. That comes out of something else that we don't know. Guarantees only hold for the deterministic model. We need to explicitly incorporate uncertainty. But the problem is now, the optimization problem is now imposed. What am I minimizing? This risk can be anything. What do we mean to optimize or even enforcing constraints? Maybe we can use expectation and chance, which is what fairly common thing to do. So we might stick an expectation behind the cost function. So average out the random variable. And we might say, okay, I am interested in satisfying the constraints. It's something that people would say with high probability. Okay. But this can be problematic. So again, this problem becomes, or for any interesting problem, becomes non-convex. And the worst bit is that it doesn't quantify how bad it's bad. I'm going to give you an example briefly. And again, to foreshadow, it's an incoherent risk measure. Okay, let's just go spend some time on this. How bad is that? Imagine I claim that I am the best financial advisor ever. If you come and give me your money, I'm gonna return it to you. The amount will be quadrupled in 2 months. And I'm very good at my job. I think 95% of this case. Will you give me your money?
What happens if the other?
Exactly. What happens if you go to jail and you might be killed? So this is an example of the downward risk is really high. This formulation is exactly the scenario again. You're going to get a lot of money, and there's a 95% chance that you're not going to lose anything. But when things go bad, they really go bad. So that's why I think for critical systems, and especially those that the performance can be tied to money. And I know that we don't assign monetary value to people's lives, but insurance companies do. So we better use the tools that they use. This sort of axiomatic risk theory. Now I'm going to run you through the tour de force of axiomatic risk theory. Okay? The variables here are costs associated with the random. I'm going to give you more specific examples. There are 4 properties, 4 axioms really, that the risk measure, this is what we want to use, need to satisfy, so that we call it coherent. Monotonicity. If something is cheaper than the other thing, if it has lower risk than the other. Translation invariance. If I have a pile of cash, it doesn't really change values. So it's translationary invariant. Positive homogeneity. The risk of having these units of money is the same as these units times the risk of having the same amount. Sub-additivity. Risk of investing 2 things together should be lower than or at most equal to risk of investing each of them individually. Yeah, I will go through them again. So it's coherent if it satisfies all these 4 measures. And really is the natural properties of a risk measure that can be translated to money. So the first one, monotonicity. If the cost of operating a system really to achieve something is less than another, no matter the conditions, then it is less risky. So if this is a safer car, then in some underlying measure, but under different conditions, then the risk of operating the first one is less than the other. If this is money, if I have a pile of cash, my risk doesn't change. Scaling the cost would scale the risk. As in changing the units of cost requires a risk in the new unit. The change of, we can arrive at it from different perspectives. The change of measure, it's just the first interpretation is put in. This is the least straightforward one. It's a risk diversification. If you diversify, if you hedge, your total risk is better than running things individually. Of course, the exact interpretation is possible. All right. So to evaluate it, we need probability distributions. But in practice, we never have the real distribution. We only have observation. We have data. So we have to estimate whatever we have from the data. So that's the framework. Distribution robust optimization explicitly incorporates this meta-uncertainty in the probability distributions themselves. And it leads to things that are kind of tractable. You know, we cannot state super general statements. There are different ways of thinking about the problem. Is that this is what stochastic optimization deals with a particular distribution we do things. In a robust optimization setup, we look at worst cases. So we try to put things in bounds support. In a distribution robust setup, we push the uncertainty really on the distribution itself. We don't know what the distribution is. What is one of these ones? It belongs to this ambiguity itself. So there are different ways of coming up with ambiguity sets. You can use moments to define them. Okay, I'm interested in all this distribution whose first moment is this, I don't know, second. We can chuck as many moments as we want to. We can put ranges on it. We can enforce some symmetry, support, locality, etc. That's one way of it. Another way is to use a divergence or distance measure. We can use KL given a reference distribution, all the distributions within its neighborhood. Of course, it's not a real topological neighborhood, but again, you know what I mean. Again, different measures of measure is not right as well. Different things that you can calculate. Now, what happens is distribution risk measure. It's a good coherent measure. It really inherits the coherency of the original measure through this operation. So what if this was coherent, this one would be a coherent measure. So we can bring it in. So what the problem ends up looking like is we end up minimizing something as a function of that ambiguity set. I'm going to stamp then. While ensuring that the risk of violating it is less than some epsilon. So instead of talking about probability of things satisfying, we assign a risk measure. And because it has this correspondence with the money that we can lose for those things. Okay, so now that's another way of thinking about the problem. You have, again, this is exactly what we saw. Okay. And we can now try to incorporate the things that come through the bad decision that we make in the estimation process to be incorporated in the risk of implementing a control as well. But as I said, because it is a distribution robust notion, so we have to take samples. So in a way, we can try to start, we need to quickly have a controller that can be queried by some planner. That can achieve.
Yeah. Oh.
Okay. So that's the second bit. Now, in the talk this morning, Andreas pointed out why global optimization doesn't work. I'm going to do a bit of an exercise why it doesn't work. Okay? Could that no one? Yeah, I don't know. Let's see. Imagine I want to solve a very simple optimization problem. Minimizing fx. And the constraint set is each variable is between 0 and 1. I know that f is Lipschitz as well. So if I calculate the difference between two different points, it's upper bounded by some scalar times the distance of those points. And what I do is the most intuitive thing I can ever do. I can go and partition the space into a grid, p plus 1. So there would be, so p plus 1, along the axes, p plus 1 points. There will be these many points. And then go and evaluate f across all these points and pick the smallest value of them. Okay. If you evaluate it, so the first question we can ask is, how accurate can I be using this framework? Maybe think about it for 2 minutes and write stuff. So one thing is that, I mean, I can never be sure that I will find the optimal value. I will go to a neighborhood. But what is the size of that neighborhood? What is my suboptimality get?
Bounded by the Lipschitz constant ratio.
Yeah, that would be, it would relate on how quickly the function value changes and how many discretization points we have, right? So it would be the answer. So we go to something that is proportional with L, inversely proportional with respect to P, and proportional with the square root of the dimension. How the proof works, it's fairly simple. So imagine the thing that I don't know, x star is the global minimum. And there would be, for construction, there would be 2 points, x and y, grid points, such that we have this perfect order. The first thing is I know component-wise, entry-wise, the difference between xi and yi is 1/p, because I have partitioned the space. I can always find possibly a third point in that square grid, I call it x tilde, that it's either if really in one dimension is closer to that corner, that would take the value of y, otherwise it would be x. So this is the closest point to the optimal solution. Okay, so it's really, so if I put another line there, this is in the smaller square. The worst case distance of the smaller square is this line connecting the center to the corner. So that's end up being the solution. So that would be the square of the norm bounded by this. And then from here, I know this is bounded by this, bounded by this, because this is really the real minima. Bounded by this, and we already knew that that's the square. Okay, very good. Now, what is the use of this exercise? I want to make a point about how hard it is to do global optimization. Yeah.
I guess it gives you a bound on the error, so you can show the speed at which it converges.
Yeah, it really does. Let's be a bit more specific. It really gives me a recipe of how many discretization points I need if I'm interested in an epsilon accuracy. So we need a uniform grid of these many to have an epsilon accuracy. It's really just the inverse argument. So set equal to this, the rest really follows. You can even make it a bit tighter. But it's terrible, really. It's n to power n. So if L is 5, n is 10, very small problem. Epsilon is 0.01. You need these many function evaluations. So it's, I mean, it really shows my slides are outdated. That was the top end MacBook then. It's probably now maybe 7 times faster, but divide that by 7, yeah. Roadrunner is not even the fastest computer anymore. There's a Chinese one, but again, let's assume it is how, doesn't matter. So this is a sort of, this is why this opens. And fight the edge of looking for global solutions because it's hopeless. It really is. What you really want, you want a useful local solution. Almost anything that you do. Okay. Cool. Now let's go back to this MPC business. Now I've done all my magic. I've turned my uncertain problem into some deterministic problem again, or I didn't hear it from the first place. In the first place, then I have a deterministic problem. Let's just go back to it. And assume I have a dynamical system, x dot f x on u. I have constraints, and I might have stage cost and terminal costs. So what we are interested, major problem is solution of the finite time of control problem. Ideally in real. Again, real time in a technical sense has a very particular meaning. So if anyone has worked with real-time systems or embedded systems, they know. If you haven't, so I can keep using the literature. So there are different ways of getting around it. We might want to maybe pre-compute the solution. So really build a lookup table. So sometimes problems have this structure in quadratic problems with linear dynamics. They have this property that their solutions are parameterized the piecewise linear function. But then you have to store all these weird regions that these piecewise solutions stick around each other. That's explicit. You can approximate them using approximate. But you can come up with some approximation. You load them in your memory, and whenever you want to find a solution, you just look it up. So the complexity is you upload it to some pre-computing, and then the recovery from however you store these solutions. How do you do the certificate? So that's one way of doing it. Okay. The other one is to really exploit the structure of these programs. What is the most important, from my perspective, how do you know? You should guess that. Important property structure that we should use when we deal with dynamical systems. Time. Arrow of time goes in one direction. So we should use that. Whenever I now talk about this, in the absence of anything else, there might be other sparsity structures. But for this sort of generic setup, so really the temporal, sorry. So that's the problem. And here I am talking about an algebraic representation of the constraint set. But early on today, I talked about X or here Z doesn't matter, in a set and U in a different set. So think of these as the algebraic representation of those. Not all algebraic representations are equal. Especially again, if you go back to this morning talk, when we care about constraint satisfaction, some algebraic representations are better than the others. But let's not worry about that too much. So I moved from geometry, but geometry, well, it's useless, really. Don't tell it to geometry. I mean, they are beautiful objects, but no one can do anything with them. So anyways, this is the algebraic representation. Again, a bunch of algorithms that people might use. They can use SQPs to solve these. They might use first order methods. They might use zero point methods. We can have different reformulations of these problems. Particularly differential dynamic programming is what I care about. Spend more time talking about. And if I didn't have the constraints and the dynamics were linear and these things were quadratic, I could use LQR solutions. And really the use of these are repeatedly solving them so that we can come up with an MPC implementation. Okay. So when I talk about dynamically feasible solutions, let me go back. I know my solutions come out should be consistent with the dynamical system. And that's where this equality constraints really, where it comes from. not from the behavior of the dynamical system. So when I talk about them being feasible, I want my solutions to be consistent with the dynamics of the problem. That's what I mean by dynamically feasible. Now, generically, when we terminate an optimization algorithm early, that's never the case. But this is what that's what it is. But these sort of dynamic constraints are satisfied in the way. Okay, so there are different ways to get around it. We can propagate the dynamics for the obtain control solution. So we can get a solution, and then so we can get the inputs, and then don't use the state solutions that we got, and then just propagate them through the dynamic. There's no guarantee that the states that come out of this they satisfy the constraints anyway. It's a bit silly. The other way is to eliminate these variables by substitution. So go back here and then replace all the z with f of z and u starting from the initial condition. Well, it's a mess. You will end up with a lot of function composition. Okay? So you really just make things tough. The other thing that you lose. Okay. Now, this is important, right? Especially if you haven't thought about control systems. How does zt plus 1, what zt plus 1 depend on in terms of other variables? Only zt and ut algebraically. Now, what happens if I do the function compositions? It will depend on everything before it. It becomes explicitly. It dependent on all the use from the beginning till that point. Again, in a very superhanded way, the first property has a sparsity. There is a structure, there is a sparsity structure there. The second one scans everything, depends on everything else. There is another way people call it state was Newton. I really don't understand it, so I do not say anything about it. The last one is, I think, is state was Newton as well, but the different interpretation is DDP, which I'm going to talk about again. Before we looked at it, there was a big problem with having inequality constraints. That was the reason that we started looking at it. So originally, again, David Main in the 60s proposed it. And then Andrew Jacobson did some stuff in the late 60s, early 70s. And Yakovich had some of the proofs in the 80s. Then it stopped up until late mid-2000, where the robotics community discovered it as a way to have inputs for different robotic systems. And then there was a frenzy of activities. Almost everything they use is still first order methods. They use the proximal methods or augmented Lagrangian. Okay, so what is the idea? Okay, this is just some other thing. So these are the common ways of solving it now. SQP, we end up building a sequence of quadratic models of the problem. It's a popular method, but it has significant computational costs and reading again for when you have constraints. You can have penalty and augmented methods, again, they're first order methods first of all. They don't use all the structure you have. The constraint satisfaction is more like they cross their fingers. And then there are interior point methods, which is really going back to we end up forming a KKT system, perturb it, and then we push the perturbation to zero. That was the new variable. It is very appealing and remarkably successful in practice. The common criticism of it is hard to understand. Well, life is very hard to understand, but it's not as hard as many other things to understand. My favorite text is this book by Renegar. It's a 100-page book. It's fantastic. A bit more on the applied side is Steve Wright, not this other book. And I really recommend Andrea's paper as well. I spent a year with this, with one of my postdocs. The good thing about this is very theoretical. This is a bit more applied. This is a continuum of how the challenges that you start observing, the more you try to. And if you really hate yourself, go and read Nemirovsky and Nestrov's book. I don't think they have read it. I've tried, I just can't get past it. But they proved the main result after 40 years, except Karmakov, which proved something in the early 80s, for the general, more not really general, for a bigger class of functions, they are the other ones who proved it. But Renegar has rewritten almost anything in a very readable way. Okay, now, where we are, we want to solve a finite time optimal control problem. Just looking at the structure that we saw, we can use purely primal methods. So think of them as projected gradient method. Now, how you can do the projection, it's a different story. Or you can form the Lagrangian and try to somehow solve the KKT system, either using a proximal method or a pure dual, which is a sub-differential method, which is using just a dual club and a dual. In a strict sense, you will go somewhere, but we don't know what that somewhere is. And we don't have, again, this morning, you remember there are these complementary conditions in KKT, and that's the bane of the first order method. The other way is to use this dynamical system property of the problem. So what I'm talking about is not for a general purpose problem, for a problem that has these dependence in common. You can use the Bellman optimality principle. You end up with a bunch of nested problems. You're going to see them. And then you can, almost similar to the other branch, start constructing different solutions for the problem. You can have augmented Lagrangian versions, or you might end up with this sort of primal dual methods of the type that we're interested in, like the interval. Sorry, the other thing is that one of the other primal dual methods is forget about that this problem comes from a dynamical system and use any interior point method solver you use. It sits here. Okay. So how we can do, just again, think what I said, in each model predictive control solution, we need to come up with a solution from scratch. Again, one problem is the most efficient way of solving this problem using interior point method cannot be, at least I don't know if it can, I think it's impossible, to warm start them. If you warm start them, they will slow down. So we need fast convergence for the real time capability. So what we want is really using, again, apply the domain knowledge or structure of the system. The problem, use Bellman's optimality principle and try to change the problem into a sequence of nested minimization problems. And it has an added benefit. It gives us a feedback form. Okay. So this is a problem that we have. We have a bunch of constraints. We have stage-wise. And how many of you have heard of Bellman principle? So what it is, again, super handy, is when you have a cause which is coupled through something that is unidirectional. You can start from the end, find the best decision you can make then, and step back. Because anything else that has led you to that point is very irrelevant. That's the basic for the shortest path problem. So that's how it really started, like the extra. Bellman formalized it. It can apply to anything that you want. Pick anything that you want that has this sort of unidirectional dependency, and you can apply Bellman things. So what it really does is that we can start at the end. So we can end up with this nested solution. I start from the latest optimization problem, solve that, feed it back to the previous step, feed it back to the previous step, and go to the beginning of the chain. Now, how can I move from this sort of nested minimization into a nested min-max problem? Is through formulating the Lagrangian of the problem. Because, again, take it from me. If I put both my primal and dual variables in the Lagrangian, I'm really solving a minimax problem. I'm maximizing with respect to, I'm maximizing with respect to the dual variable and minimizing with respect to the primal variable, but I press minimum. Now, this is interesting because we wrote this thing a few years ago. And I noticed that a lot of people were not interested in, and we wanted to have a global convergence group. When we talk about global convergence group, it's really whenever you initialize it from wherever, it should go to a local solution. That's what I mean. So I know exactly what this paper is lacking, but a bunch of venues that are double blind, they end up with these arguments with me that this paper has already solved this problem. And I just can't say, I know it hasn't. I don't know who are you? So it's been proving very hard to publish the full version of the paper, maybe one. So the problem looks like this. Again, a bunch of nested problems. The good thing is that because it's finite horizon, it's finite recursion, and we start from the end. This is the last problem. Okay. And that's the terminal part. Okay. So the idea behind any differential dynamic programming method, the first idea is that we have a recursion from end to start, and then we propagate information that we have from the beginning to the end. We have these basic questions we have to answer. How do we resolve the recursion? How do we update the solution? And when and why the algorithm? And when I say work is that should have the guarantee that we get the feasible solution and the locally optimal solution. So the graphic representation of the algorithm is like this. At any stage, this is everything in the future, because as the information comes from the end, we can put them together and call it, if you want, call it a value function. If not, just it's the exact estimate of the tail. Given this problem, we want to solve this minimax. Here, what I'm really doing, I'm coming up with a local perturbation to the current solution to solve the minimax problem, and then use those perturbations to update my previous value, and then repeat it, go one step back. Okay. Not SE. These are my diagram multipliers. Now V is, if I write its Taylor's expansion, it has high order terms, but I truncate it as a quadratic function. So I use the quadratic model as my cost to go. And how I construct the model, I start from the end. So Vn is the final value function. As I said, to go backward in time, exactly is the same thing as the terminal. Yeah.
I think you explained it on the last slide with the perturbations, but don't you need the final state in order to evaluate the final min-max?
You find the final min-max as a, yeah.
Without knowing the final state.
You start from a guess.
Okay, so you go.
You find, yeah, exactly. You find the guess for the final one, you update it.
Yeah.
You come up with an initial guess for everything. Okay. And then you use that to recursively update everything backward, and then propagate a new one forward.
You do multiple passes?
Yes. Yeah. So each backward and forward pass is equivalent to one step of full interior point method.
Okay. And the perturbation is the correction that you apply.
Exactly. It's the update. Okay, now this is the quadratic model. I just wrote it as, this is something commonly known as the Q function. So if anyone reads reinforcement learning literature, that's what we see. And that's what they do. Reinforcement learning is the sequence of Bellman operator and NPC. They call it rollout. And there's a reason that, again, these are historical. Dimitri Berserkas writes a paper every 6 months. It's almost the same, sorry, write a book. It's almost the same book. But if you pick any of them over the last 10 years, there is a good explanation why the relationship between optimal control and the Frank Lewis has a series of good books to play. I got sidetracked. So then we end up, yeah, as I said, optimize with respect to these variables. Again, we have this S appears, this is the multiply. This is the perturbation. So we end up solving this perturb system. So the choice of U, it keeps solution away from the boundaries. It's really just the log barrier equivalent. And make problems smoother in a way. And again, we saw versions of it. And as it changes, we follow them to the path. It controls the convergence because how closely we follow the central path, and allows us to make sense of optimality and the complexity of the problem. This is how we update now the quadratic model. This is now the future information is propagated to update the new model of the previous step. These are the way the updates are related. Now, these things are equivalent of step sizes. And once we go to the beginning and calculate all these alpha t's and beta t's, these are the full update rules. We use them now to come up with new. So the superscripts are the iteration updates, the subscripts are the time stage in the algorithm. So that there are two indices really. So these are the update. The new ones are obtained by these update rules. So which are these updates? The one without, this is what we feed it. And this is the previous estimate for that state. Now, the biggest challenge in the analysis of this initial is, as you're doing the update, it's not as if that we don't update all the variables using the same set of equations. The update rule has this dependency as well. So coming up with a way of doing line search was very difficult for us. Because do you reject a particular stage because you don't get enough sufficient decrease? But maybe if you stick with that step size, everything else would have decreased much more. So that was a bit of a challenge for us to make sense.
So the F at the bottom, is that an integrator then? The integrators then?
Yes, this is the dynamic. The integrated
so
forward and
integrate
dynamic. Yes.
If you do like backward pass, I guess when you finish your backward pass, you have to do it ends up on real-time version, real-time value.
No.
No? Okay. No,
You
you're
go-
trying to get back to.
Now you go backward and forward, and each pair of backward forward paths is one step of the algorithm.
Okay.
It's like one iteration.
But we're not necessarily in the case where we're doing like MPC where I have a non-starting point measurement set.
So now this, for each version of the problem, that's our optimization algorithm that we use
Okay.
to solve the problem.
Okay.
Now, there is a benefit to this. The real benefit is the solution that we obtain comes with this. We call it the feedback form. So if you didn't have time to finish your calculations, you can use the previous feedback form to update your current, to come up with, assuming things that change too much, you can run your update of the algorithm open loop while the rest of the algorithm is catching up. Again, in the old literature, these things are known as influence functions. Now, that doesn't mean anything anymore, because it means something in neural networks these days. But what it really means, it's really like the implicit function theorem. These determine how sensitive your solution is to perturbing the state that you're at. But in optimal control literature, these sort of things were known as influence functions. Okay. Now, what we can do is, so this is the simplest case. We start with a bunch of feasible solutions. We can show that we go to perturbed KKT points. As the perturbation goes to 0, we go to the real KKT points. We need constraint qualification as well. With line search, regularization, and step filter, we can have global convergence. We can have local quadratic convergence to the solutions. We get these feedback control laws if we can't solve the problem fast enough. We can relax these assumptions, yes. Really, the the biggest challenge was the sort of step size selections and the step filters, line set and step filter. Took us some time to figure it out, really. Now, what we're going to do now, we're going to start from there, derive a bunch of equations, then see how we can solve an optimal control problem. I stayed late last night to make this for people. Now, just before, if anyone wants to run it while I'm doing it, you can go to this OpenMPC repository. It's maintained by Mikael Johansson out of KTH. I think it's a very handy tool. You have to muck around a bit with the Mosaic solver if you want to. And then you just have, if you follow that, you're fine. I ran it on Linux. It worked the first time, so I didn't need to do anything about it. There is a second example I'm going to show you solving the same problem using an DDP, the filter DDP algorithm. It's written in Julia, and that's the repository if you want to test that as well. There is this notebook that you can use. The notebook was a bit buggy on my computer, but maybe if you run it, it's going to work. So it's up to you. If not, just let's go for the right then. All right. So we want to come up with a model, dynamical system model of that, and then see what we do next with it. So what is it? Does anyone know what that circuit is? It's a converter. Does anyone know what specific converter that is? It's a mid-switch. Now there's another way of drawing it. So to think about it, this is another thing. For some strange reason, many years ago, they asked me to teach electronics. So I learned all sorts of things that I didn't know I would ever learn. So the way that the converter works, transistor Q1 turns on. So Q1 and Q2 operate in complementary signaling. So when Q1 is on, Q2 is off. And when Q1 is on, diode 2 conducts. When Q2 is on, diode 1 conducts. How would we usually implement the switching between these two switches? What is the technology? How do we, transistors are how we implement the switches, but how do we drive the switches? We have a gate driver. How do we drive the gate driver? Yes, PWM, right? They have a pulse width modulation that we are going to implement. So how does, for those of you who don't know what a pulse width modulation is, it's...
Yeah, you see there.
Oh, yeah.
Yeah, those really screen. So you control that they're like that.
So a PWM signal it's a periodic signal. I'm going to hit my board soon, but it's a periodic signal. With a switching time interval, Ts. So Ts is 1 over the switching frequency. Usually we operate in the orders of 10 to hundreds of kilohertz. So this is 10 to the power minus 4, 10 to the power minus 5. So the way now, when it's high, it turns one of these transistors on, and when it's low or its complement is high, the other transistor turns on. So what we have here is, I use capital B for it. There is a duty cycle. Interval 0 and 1. So for a bunch of the interval, we are in a high signal, then we are low. Okay. Now I was going with that. Some here. Okay, now. So if I look at this and this, I don't know. This is something that I've noticed in Australia and in the education system. It's forgotten. Does anyone remember from circuit theory what these variables were called? The current of an inductor and the voltage of a capacitor. Yeah, they are states of the circuit.
Yeah.
Now, why are they states? Because they contain all the information you need about the circuit. Circuits are dynamical systems. Okay, so that's one thing. There is something more interesting happening here. If I ask you to write the dynamics of this particular circuit, how do you write it?
Through Laplace.
Laplace works for linear time invariant. Is it a time invariant system?
You do like a state space.
But how do I, before that, but it is a state space, I've written state, but how do I write it in a way that describes the behavior of the system completely?
In Laplace space. Frequency transport.
No. Okay. I'm intentionally being a bit difficult, but okay, let's just rewrite this. I like writing things in terms of x. So I'm going to define my x as I drop L. There is no other current that I'm interested in, and B. So for this time, I write x dot equal to A1 times x plus VGM. Okay. And I'm going to put them together. For the other one, I write it as x dot equal to A2 x. Sorry, this is wrong. For any time in the interval I'm just going to bring this K. Because again, I said it's not a periodic signal. Well, I can look at a bunch of blocks. This origin is arbitrary. I put it at the multiple of Ts. It's a switched dynamical system. What is the input? It's D. No, the input VG is the source of the circuit. So that's where, again, what's the meaning of input to a system? D is the input. But it looks a bit weird. Right? So this is what a hybrid dynamical system would look like. Sometimes the input sits somewhere there. Now, to make it tractable, what people do? They do circuit averaging, or do an averaging operator. So if you do that, I have to really imagine an arbitrary variable y. I call it y bar, and that's its average. I do a centered average. There is a very specific reason for it. The reason is, does anyone know what a notch filter is?
Yeah, what's the remain? It's a function of that high pass and low pass, you want the remain frequency.
A notch filter takes filters a particular frequency, maybe harmonics of a particular frequency. This looks like the averaging operator looks like a notch filter. So what it does, it gets rid of the harmonics of Fs. Why is that? Because we have these hard edges. Introduces a lot of really unwanted dynamics that probably get filtered through the natural properties of the circuit. And they don't contribute to any salient property of the system. Right. So the derivative of time derivative of the average signal is the average of the derivative. That's why I can write things in terms of, let me write it up somewhere. So how do I take averages now? Is the DTS length times on is one of them, the other one, the complement is the other one. When divide everything by TS, the whole thing disappears. So it is really this. dA1 plus the rest of the interval A2. Now this is x bar plus D times, let's call this D1. E2 and that. So I write everything. I call this guy A bar becomes A bar X bar plus. So the average model is a linear dynamical system. Now, what are the constraints on D? D, 0 and 1. What are the constraints on U bar? Yeah. So I ended up with a dynamical system that has a very benign look to it. So where did I do approximation? There is no approximation in the switch model. I did the approximation when I looked at the average. So this is my dynamical system. Now let's see. Not that, not that, not that. Yeah. So this is just what I need. Now I'm going to set up a circuit. I'm just assigning numbers, right? I'm I'm assuming L is 5 10 to the power minus 4. So 50, no. Yeah, 50 micro Henry. Yeah, so sounds about right. No, 500 micro. And then the capacitor is, that would be 100 microfarads. And the load is 50 ohms, and the voltage is 50. It doesn't matter which. It actually matters. But now, why would it matter? Why would the choice of the capacitor and the inductor and R matter?
So the time constant.
Yeah, time. Everything should be fast enough so that when the time scale we operate actually makes sense. Otherwise, it would be a funny thing to see. I wanted to say something else. Yeah, okay. Now, before doing any of those analysis, one use for H-bridge is the most basic inverter you can ever imagine, to turn DC signal into AC. The way to see it is that let's look at the fixed point of this. Is it the one? So what I really care about maybe is the output voltage. It's the second element. If I write, and then there is a VG there too. So if I look at the second element of this writing everything, it ends up being V is equal to VG times 2D minus 1. Okay. Now, if I go and modulate D, sine or cosine, I just write sine. Frequency in Canada is 58? 60. I'm used to 50, so. If I modulate the signal like that, and I plug it in, what do I end up with? 2 times half is 1, cancels this. It becomes. Now, what is fundamentally problematic from just reading too much into this? It's a steady state behavior. I'm forgetting that things might go wrong, everything, right? It has no dynamic to it. So that's why it can be used as a as an inverter, DC to AC inverter. Okay, now, but our goal is something else. Our goal is now to design a control input so that the particular output we are interested in is sinusoidal. So I'm going to define something called a reference signal. Vref, let's assume it's VG sine, again, 125. Okay, that's what I want to achieve. So what would be a sensible objective cost function? So it would exactly it would be V minus this Vref. Cube. Yeah, not cube. Over some horizon. And that would be the error, right? Do I care about anything else really? Probably not. I care about my input should be constraints. Maybe I have safety inputs on the voltage and the current of the inductor as well. But that's the most basic problem. So there is something I have. That's my measure. That's my constraints. Now, all of these things are continuous time objects. what is the simplest discretization that I can think of? It would be an Euler discretization, right? With that sampling frequency. So what I would do, because that's the quanta of time. We are doing quanta of time in making decisions about my controlling. So I need a discrete time version of the problem. I would never run out of this. I call it tilde. That's a discrete time variable. Is I plus Ts times A bar x tilde plus Ts B U bar. I'll just call it U bar. So that's my discrete time, the next time step. So that's my, this is my dynamical system model, the discrete time variable. So these are just setting up the problem. I'm running it for 0.05 seconds. We are talking about hundreds of kilohertz. That's long enough. That doesn't matter. So, does anyone remember what a zero order hold is? Don't worry about it. We keep switching between these two dynamical systems. So how do I simulate it? Because I still have to, that's one thing, right? I have a I'm not modeling the system exactly as that. I'm modeling it as that two levels of approximation. One through averaging, and then discretization, time discretization. But the underlying system is the switch system. So this is why I have these two functions, interval 1 and interval 2. They are just initial value problems. Given starting at some point, we have to see how the system propagates in time. So that's that. I initialize, oh, maybe I can do that. Z is just a trajectory. Don't worry about that. Don't worry about that. This is just keeping track of stuff. These are the A and B. And that CS selects the second element of the state vector, which is what I'm really interested in. Okay. Don't worry about this. D is 0. It just has to be there. So this linear system object comes out of that OpenMPC package. Now I'm defining cost. My running cost Q is 0. I don't care about states changing. My R, which really penalizes my control input, is 0. I don't care what cost I apply to my control. My horizon is 3. Ridiculous. What works? I set up the problem. I just invoked Mosaic because I had to fill out forms to get the license, so I had to use it. I bound the input to be 1 and -1. This is just, don't worry about it. Don't worry about that. Set up the problem. And then I'm running it over discrete time steps that I make decisions. And this UT-MPC tracking get control is the first step out of the optimization problem, MPC optimization problem. And again, remember that the problem set up using these dynamics and these things it's a simple quadratic model now. It's convex. It's as nice as it gets. And then this is just the initial value problem solving for the two intervals with a fixed D at the beginning. Because what I'm assuming is that I'm updating the duty cycle at the beginning of its switching interval. And then concatenate solutions, put them next to each other, solve it. Now, let's run it, and now we're going to see an error problem. Let's see. I think it worked, please. Okay, I'll go here. Okay. The green and the orange now are on top of each other. Green is the reference, orange is what it was. Okay, so yay, it worked. Surprisingly. But now let's just go and make this 2. Sorry. The horizon is just 2 steps ahead. Yeah, I mean, we always move it like that, right?
Only 2 horizons.
Yeah, yeah. Okay. Did it run? Yeah, finished. So you see, now I am a bit out. Okay. Now, if I want to see, it's just about getting a sense of what are the important bits here. So now if I go here now, the thing that I said, don't worry about it. Now, what is the glaring problem with this?
You're a little stunned.
No, that's okay. Okay, I'm nothing. Okay, that's not the problem. I'm running a simulation for 0.45 seconds. Just it's certainly longer than 0.05 seconds. Oh, didn't work. Good. I mean, it worked. Anyways, if you just change the variable, you end up breaking it. But this is a very simple problem with a very simple structure. It's very hard to break it. Okay? Now, the biggest problem is time. How much time it takes to solve this problem. So we can go and use something slightly fancier, which is, if I can find it, here. So this I only solved one step. And a lot of the time here, okay, this is where the overhead in the beginning is wrong because we are compiling all the derivatives and the second order derivatives. So that's why it's better to use it. It solves each instance at least 1 order of magnitude faster than the other method I using also. But still, the problem is it's not fast enough. It's 18 milliseconds for solving one iteration.
That 18 milliseconds doesn't account for the.
No, it doesn't, but it's even if you account for that, it's probably can drop to around 5-6 milliseconds, still not fast enough. Right? On a general purpose computer, and most of it is compiled. Probably if you do it in C, it would be faster. But it gets to a point that you have to really operate at the same frequency. So your hardware should be bare on operating at the same frequency as your chips. So that's why there is a push to have FPGA type solid gate. And especially for the problems that you can get away with the simple formulations of the problem, you can write solvers very compactly on FPGA.
That's how they do real-time simulation for.
Yeah, exactly. So if you can get a lot of money out of OpenRT to implement it for them, do it. Or you can hire me. But anyways, that's one thing I wanted to show you, right? There are multiple levels of. You have to come up with a solution that solves the problem you have for the specification of the. A practical implementation is to. So, for example, we know we can reliably solve every 5 milliseconds. So we don't use just the first input. We use a whole bunch of blocks of inputs while to buy time to solve the next instance of the problem. So that's something that you can do. You can do the sampling. The model can be still at a faster time scale, but the solution can happen at a coarser time scale. That would probably work here as well. I was tired last night. I couldn't even. That's that. Now, let's go back to this and finish. Yeah, I'm on 7. So. And if Tobias Geyer, as I said, he's someone who has been playing with these things. The way he writes MPC really doesn't approach it from this perspective of writing the duty cycle. He writes problems in terms of discrete variables, in terms of positions, especially when you have this multi-stage inverter, these different stages on and off. That's how I write it. I mean, he knows more about this. But I think a lot of the time, they're probably unnecessary. You can get away. As long as you do your feedback implementation fast enough, you can get away with a lot of shoddiness in your modeling. And the observation is that the THD becomes much lower when you have this fast. Is the distortion, the harmonic distortion, is much lower when you have these fast MPC solutions. At least that's the observation by the Tobias Geyer. Now, just something else. Is a bunch of statistics about one example. Again, there is a danger to read too much into one example. But that's how we tested it on some control problem. The reason that it's almost identical to IPOC in terms of implementation. The reason that we perform slightly better is that we are explicitly using the structure of the problem. We're not a general solver problem, so you expect that by putting more effort, you're going to get more out of it if otherwise it's fun, right? And we had this discussion. You know this iPod with B in front of it? That's the most common version of the solver that people use in robotics, and that's not how they should use it. But it has somehow that became the easiest thing for them to set up. Yeah, I don't know what talk to them.
People are lazy and don't want to.
Yes, probably. That's what it is, right? Because you don't need to take care of the second order information. That's so it's bizarre. It's sometimes when you talk to them. And then the most right answer thing is a first order method, is a proximal method. Which again, I think it's crazy. If you, I mean, first order models are useful when you have really some very particular structure, or you care about distributed implementation of your solution. Because it's an open problem as well. You cannot solve SVD in a distributed way. So if you could, that would be good. More. So another thing, if anyone ever wants to read guide for perplexed, that's my favorite code out of it. But it's about universality of God or the Newton's method. Whenever in doubt, use the Newton's method. I preached that school of thought. I start from last. Panaceas don't exist, except it's Newton. That's a different story. You do not need an exact model. That's why we use feedback. Most of the time, we want to avoid making really bad decisions. That's why we have this constraint satisfaction. So from my perspective, constraint satisfaction is what really important. And then depending on which level you operate, you have different information and computation requirements. And explore the structure whenever needed. I'm a bit worried about talking about information, but there is a lot of interesting things to be said if you care about the information content of your decisions. And I dare to say that sort of view should be applied to power systems as well. I'm going to blaspheme it. Power systems are signal processing systems. Your information content means different things. So it's the same principles that people do for signal processing, by and large, should be applied to the way of they think about power systems from my perspective. We have filtering is the same. What you want to do with your signals is the same as well. You want to have low distortion. That's a communication channels problem. I think there are a lot of interesting parallels, but I'm not courageous enough to give. And then there is this other question, as I said, the choice of these cost functions have a real impact on the transient behaviors. And if you ask a very old school engineer, they can look at the behavior of the system and say, this is not right. They know it through many years of observing what is a good transient, what is not. But there is a way to try to encode that information in the open control formulation of the problem. And this is what is called as learning from demonstration. And thanks to all the smart people I learned from and people who paid me money to do these things. Thank you.